All right, back for the final video that I'm going to make on thermodynamics. This video is going to talk about heat capacity and the process of calorimetry. Once again, really only going to be scratching the surface, giving you an introduction of like the terms that you need to know and showing you how the math works. In terms of going in depth on it, you may want to do a little bit more watching of things. I'll be collecting some other resources for you guys to take a look at over the weekend if you want to. But hopefully this will serve as a good introduction to the ideas and will help you out a little bit. All right. So first concept is the idea of heat capacity. I really want you guys to understand this, even if we're not using it for AP. It's something that's good to know about, maybe for college chem, stuff like that. So what is heat capacity? All right, well, heat capacity, the definition is it's the ability or capacity of a substance to withstand temperature change when energy is added or removed from the substance. Okay? So it's the ability or the capacity to withstand temperature change. High heat capacity, your substance is good at withstanding temperature change. Low heat capacity, your substance is not good at withstanding temperature change. Okay? Usually it's given the variable C when used in calculations, and the units can be different depending on the form. You're more than likely going to see this, the one over here on the left-hand side. This is called specific heat capacity, and it's in terms of grams. So the actual heat capacity, the value, is going to have units of joules per gram degrees Celsius, or Kelvin. This can also be in molar values, okay, where the gram is just replaced with mole, right? So converting from grams to moles, you could do that, okay? So both of them are usable, but you're more than likely going to see this, okay? All right. So in order to really understand like what heat capacity is, what the value is, I want to talk about water, okay? Because water has an extraordinarily high heat capacity, and I think given everything that we know about water and its intermolecular forces, we can understand it best by talking about it in the context of water, okay? So water has an extraordinarily high heat capacity. What that means is that water has an extraordinary ability to withstand temperature change compared to other substances. Okay? And I want us to understand why that is. All right? So here's a collection of water molecules. We've got 3 water molecules. We've got the little partial positive and partial negative regions labeled on here. The solid lines are those polar covalent bonds between the oxygen and hydrogen in a single molecule. The dashed lines are the intermolecular forces, right? The hydrogen bonds. Okay. So, water molecules, we know this, they're very good at holding on to one another, right? Really, really strong intermolecular forces. A substance that has really strong intermolecular forces, that has lots and lots of these interactions keeping the molecules, attracted towards one another, those molecules are not going to accelerate, they're not going to move as easily as other substances might because of those intermolecular forces. Okay? The hydrogen bonds, it's almost like glue that's sort of keeping the molecules in their position and not allowing the water molecules to move around as much as in, say, another substance. Okay? And that's why water has a really high melting point, really high boiling point. That's why water has really great surface tension. All those different unique properties of water all come from hydrogen bonding. Okay? But yeah, heat capacity is one of those things as well. So, it is the extraordinarily strong hydrogen bonds, the intermolecular forces that exist between the water molecules that prevent the water molecules from speeding up compared to substances with weaker intermolecular forces. Okay? It takes more energy per gram or per mole to heat up water than other substances. Okay? Now, you have to be keeping in mind, right? Temperature, right? Temperature is a measure of the speed of the molecules, right? So it takes more energy to increase the temperature, to increase the speed of those molecules. It takes more energy per gram or per mole to heat up water than it does for everything else. Water is like it has the highest heat capacity of like any liquid, okay? and it's really due to this like extraordinarily strong intermolecular force that that water has compared to others. Here's another problem that has some other heat capacities. Metals have really low heat capacities when compared with water. Water's heat capacity is like 4.18. So it takes 4.18 joules per gram degree Kelvin or degree Celsius to heat up water compared to these metals. Metals, it's a lot less. So this question here is going to help us understand like how we can think about these values, okay? All right, so here's the question. If equal masses were used, which metal can absorb the most heat before the temperature would increase by 1 degree Celsius? Justify your answer. Okay, before we even get into it, I want to just take the first metal here, aluminum, and I'm going to write out this value with the units, okay? So the heat capacity for aluminum is 0.897 joules per gram Kelvin, okay? All right, what this means is that for aluminum, it takes 0.897 joules to heat up 1 gram of aluminum by 1 Kelvin, okay? So to go from, say, 1 Kelvin to 2 Kelvin, and let's say you have 1 gram, okay? It's going to take this many joules to make that temperature transfer, or to make that temperature increase happen, okay? That's what this specific heat number is, okay? You know, substitute 1 and 1 here for the values here, okay? Or you can think of it this way, multiply this heat capacity times 1 gram and times 1 Kelvin, okay? Grams and Kelvin cancel, okay? That's what this heat capacity is. It's the amount of energy that is required to heat up 1 gram of that substance by 1 Kelvin, or by 1 degree Celsius. Coincidentally, guys, Celsius and Kelvin, they're the same scale, okay? They're not the same number, right? We know that to go from Celsius to Kelvin, we have to add 273. So like 0 Celsius is 273 Kelvin. Is that right? Yes. So, but they increase in the same amount of like steps. So like every time you go up 1 degree Celsius, that's the same as going up 1 Kelvin. Okay. So that's why you can use Celsius or Kelvin here. This could be degrees Celsius if you wanted, because we're not actually like this is all, well, you'll see in a second, but this is like a change in temperature, not like a raw temperature value. So with ideal gas law, you have to use like the raw temperature in Kelvin. When you're using heat capacities, it's this value here, this Kelvin, is always like a change in temperature. So it can be Kelvin or Celsius because you're like subtracting the values. So it doesn't actually matter which one you use. Okay, so back to the question. If equal masses were used, which metal can absorb the most heat before the temperature would increase by 1 degree Celsius? Justify your answer. Okay, well, aluminum has the highest heat capacity. Okay, here's how I think about it. The substance with the highest heat capacity has the best ability to withstand temperature change. Okay? So, if equal masses were used, which metal can absorb the most heat before the temperature would increase by 1 degree C? It's going to be aluminum. Okay? It's got the highest heat capacity. You have to put in more energy per gram degree Kelvin to increase the temperature, right, than for any other substance, okay? So like lead, 0.129, you only have to put in 0.129 joules to heat up 1 gram by 1 Kelvin, or by 1 degree Celsius, okay? For aluminum, you have to put in 0.897 joules to heat up 1 gram by 1 degree Celsius, okay? So lead is going to be the easiest to heat up, then cadmium, then iron, then aluminum. Okay, aluminum is going to be the most difficult. Okay, so how would we necessarily justify our answer? I think what I would say is, so my claim would be aluminum. Okay, My evidence would be aluminum has the highest heat capacity, and then my reasoning would just be describing what heat capacity means, right? Aluminum has the highest heat capacity value. That means that it would take 0.897 joules to heat up 1 gram by 1 degree Celsius, compared to these others, which would be easier, right? So which metal can absorb the most heat? It would be aluminum, because it would absorb this much compared to these others. So, okay, that's heat capacity in a nutshell, all right? You're going to be using heat capacity values in this equation, okay? This is the most important thermodynamics equation that there is. It is the first equation in the thermodynamics section on the reference sheet, okay? There's two forms of it because, once again, it depends on if you're talking about specific heat capacity with grams or if you're talking about molar heat capacity with moles. You're more likely to see this, okay? All right, so what does this mean? The heat that goes in or out of a system is going to be equal to the mass of that system times the heat capacity of that substance times the temperature change, okay? The units work out, all right? Let me show you. So heat is in joules. Mass is going to be in grams. Heat capacity is joules per gram per, we'll say, degree Celsius, okay? And then change in temperature, that's like a subtraction between temperatures. So it's going to be degrees Celsius, okay? Now, if you look at how the units cancel, degrees Celsius cancel, grams cancel, joules equals joules, okay? So the units work out. This type of formula is needed whenever you're doing a problem where they are asking you, like, how does the temperature change when this process happens? Or the temperature changed by this much, how much heat was transferred? Or you've got the temperature change and you've got the heat, how much mass was there if you know those other two values? So, like, it's the type of problem where they're usually going to give you this, they're going to give you C, and then there's 3 other variables. They're going to give you 2 of them. You got to solve for the other one. That's more than likely what you're going to encounter when you encounter this type of problem, okay? So this is like a constant, okay, the heat capacity. So you're usually going to be given that value, and then you're going to have 2 of the others, and then you're going to be solving for the third one. It is possible that they could give you the Q, M, and the delta T, and they would ask you what the specific heat capacity was. In that case, you would just plug in the others and solve for the C, solve for the heat capacity, okay? All right. So let's look at where this comes in, okay? When, like, what scenario, what context would you have to do this? The context is calorimetry, okay? This is a lab method. Obviously, if we had more time throughout the year, we would do this. It's kind of cool. It's pretty simple, okay? It's a lab method that can be used to measure heat lost or gained by a system, okay? Basically, what you do is you measure the temperature change during a process, okay? And so if you can measure this temperature change, if you can measure this delta T and you know the mass of your substance and you can look up its heat capacity, then you can calculate this energy change, okay? So that's kind of the idea going into calorimetry, all right? One other thing that I do want to mention, I mentioned this before, it's not really plausible to directly measure the change in energy or the change in temperature of the system itself, right? The system is the substance, right? The thermometer is going to be part of the surroundings, okay? So, like, if we look back here, let's say the system is the liquid, right? Well, the system is the liquid. It's not the thermometer. The thermometer is the surroundings, and so the thermometer is going to be reading the temperature change of the surroundings, not of the water itself. You can't really do that practically. So when you are encountering a calorimetry problem, the temperature change is always going to be like the surroundings change, okay? So there's oftentimes a negative sign that's involved here. Okay, let me just read this. That means that if you measure an increase in temperature, that's the increase of the surroundings, okay? So the energy gained by the surroundings, or the thermometer, is equal but opposite to the energy lost by the system, okay? So if you gained energy, then that's going to be equal to the energy that was lost by the system, but there's going to be a negative sign somewhere, okay? All right, so let's look at an application of this, and then that'll be it for this video, okay? So this is that scenario that we had from the previous video, the thermal equilibrium. We've got a metal that's getting dropped into this water at 25 degrees Celsius, okay? So we're going to use this equation. It's called, some people call it Q is equal to MCAT, okay? Because the little delta here kind of looks like an A, so it's Q is equal to MCAT, C-A-T. Some people say that. I don't really say that, but there you go, okay? This equation is on your, it's on your equation sheet, okay? We can substitute these Q's for this, okay? So the Q of the metal is going to be the mass of the metal. Then we have the heat capacity of the metal, and then the delta T of the metal, so the temperature change of the metal. That would be equal to negative the same thing, but for the water, okay? So the water, let's see, we'd have the mass of the water times the heat capacity for the water times the change for the water, change in temperature of the water. Now, if you have an FRQ or even a multiple choice question where you've got some of this stuff going on, if you got like a calorimetry thing going on, or if you got like a heat transfer thing going on, they're going to have to give you a lot of this information, okay? So, for example, they're probably going to give you the mass of the metal. They're probably going to give you the mass of the water. They're probably going to give you the heat capacity of the metal. They're probably going to give you the heat capacity of the water, okay? They're going to have to give you temperatures. Look, we've got the initial temperature, 100°C and 25°C, so we can actually plug some of this in. Just for the sake of doing a full example, let me go ahead and give you some values, okay? So let's say this metal weighs 10 grams. Okay, and let's say that the water that we have here, let's say this is, I don't know, 50 grams. All right. Now, let's say that we also have the heat capacities. I'll go with a general heat capacity for metal, let's say 0.5 joules per gram degree Celsius. And let's say for water, well, I actually know what water is. I'm going to do a sort of easy version of it. We'll just say 4. Okay, it's actually more like 4.18, but it's good enough. Okay, just for some easy math, we'll say 4. Okay, so first of all, a little bit of a review about heat capacities. Water, it takes much more energy to heat up a gram of water by 1 degree Celsius, right? It takes 4 joules of energy to heat up water, to heat up 1 gram of water by 1 degree Celsius. It only takes half of a joule to heat up this metal by 1 gram. It only takes half of a joule to heat up 1 gram of metal by 1 degree Celsius. Okay, what that means is that the water, it's better at resisting the temperature change than the metal is. So if we want to think about like where the temperatures are going to meet, the metal is probably going to change its temperature more than the water is. Okay, it does depend on the mass values. Okay, but the water is going to be better at resisting that temperature change than the metal is. So that we're going to expect the metal to cool down a lot more than the water heats up. Okay? They are going to reach that thermal equilibrium at some point though. Okay? I'm going to go ahead and try to plug in as much as I can into this equation. Okay? So the mass of the metal, 10 grams, times the heat capacity, 0.5 joules per gram degree Celsius, times the temperature change, delta T, temperature change. Look at this. Temperature change, that's going to be final minus initial, okay? I don't know what the final temperature is, okay? I do know what the initial temperature is, 100, okay? This is equal to negative times the mass of the water, 50 grams, times the heat capacity, 4 joules per gram degrees Celsius. And then this is going to be times the delta T of the water. Okay, once again, I don't know what the final temperature is. I do know what the initial temperature is, 25. Okay? There's only one variable in this equation. It's the final temperature, because given enough time, these things are going to reach thermal equilibrium. Okay? This is a classic problem that they could ask you. If they give you the masses of the objects, the heat capacities of the objects, and those initial temperatures, given this formula right here, these formulas right here, you can calculate that final equilibrium temperature. Okay? This is the type of thing that you could type into your calculator with, x as the temperature variable and solve for it. Okay? Obviously, you can go through and do the algebra if you want to. I'll go ahead and do that for you, okay, just to show you how it works. Let me go through and cancel my units first, okay? So grams. Ooh, you know what? I made a little bit of a boo-boo. This should be degrees C, okay? Degrees C. All right. Grams cancel. Let's see here. My Celsius is going to cancel, okay? Grams cancel, Celsius is going to cancel. Okay, so that what that means is that this side of the equation is going to be in joules, this side of the equation is going to be in joules. That's what we expect, okay? Okay, let me actually go through and do the numerical part of this, okay? All right, so I'm going to get rid of the units at this point because it doesn't really matter. We're just solving for TF. I was just confirming that the units were going to work out there. Okay, 10 times 0.5, 5 times TF minus 100, okay? That's going to be equal to negative 50 times 4, that's 200, times TF minus 25. Okay, let me go ahead and distribute this, okay? 5 TF minus 500 is equal to negative 200 TF plus, oh boy, that's a big value. Okay, let me see here. Well, if I did 2 times 25, that would be 50 plus 2 zeros, so it's 5,000. It's probably a bit of a stretch. You wouldn't have to do that on a multiple choice section, but for your response, you could be expected to multiply those, okay? All right, we just want to combine like terms and then solve for TF, okay? So I'm going to add 200 TF to both sides, okay? So that's going to get rid of it here, and I'm going to end up with 205 TF on this side, okay? And then I'm going to add 500 to both sides. So that's going to get rid of it here, and I'm going to end up with 5,500 on this side. Divide by 205 on both sides. There we go. Okay, so clearly this is something that you would need to do, with a calculator, all right? Let's see, 5,500 divided by 205. Look at this. Wow. 26 point. Well, I tell you what, if we're sticking with sig figs, I only gave you like one sig fig, so that's probably not great. Let's give a little bit of detail here. I wasn't really thinking of sig figs when I made the problem. Okay, that means TF is equal to this. Okay, so look at that. The final thermal equilibrium temperature is 26.8 degrees. That's what I mean by water having a really high heat capacity, okay? You put this piece of metal, which is at 100 degrees C, which is the boiling point for water, okay? You put that in there, the water is only going to rise by 1.68 degrees. The metal is going from 100 degrees down to 26. So the metal is actually going to be lowering by like 73 degrees, okay? That's the difference of these heat capacities, okay? The water is much better at resisting that temperature change than the metal is, okay? And also the masses come into play, right? We've got 50 grams of water, which can absorb that heat and resist that temperature change. We've only got 10 grams of the metal, okay? So, the 10 grams of the metal, it's just not as much as the 50 grams, so it's the heat capacity and the masses that get multiplied together right here, right, which influence things. Okay, hopefully that helps. I will send you guys a video about this as well that'll have like an additional calculation or two, probably like a Khan Academy thing. But hopefully this gives you like a rough idea of how you might have to use heat capacity in a heat transfer or calorimetry type of problem. All right, thanks a lot for watching. That's my final video for thermo. Okay, so I think I kept the total time under an hour, so pretty good.